Sarah, what's up? So I'm 66 floors up in Dubai right now. Everything here is like a super crazy tall building, all man-made, all like the last 5, 10, 15 years. Biggest building in the world is here. That's the Burj Khalifa, 208 floors, or 206 floors. It's 585 meters. I'll let you do the calculations how many feet that is, but it's pretty darn tall. Went up to the top the other day, not the tippity top, but as high as you can go, like 160 floors. It was pretty impressive. Let me know, I'll show you a picture from up there. Dude, like all the buildings look like they're like 10 stories. And I'm talking like 30, 40 story skyscrapers looking like they're junk. That's how crazy this building is. But anyway, now, in this video, I want you to be all caught up with chemistry, and I helped Bryn out, and there's more electron stuff. So I'm gonna get you all good to go on that. It's pretty easy. I know it may seem like overwhelming, but in and of itself, it's trust me, it's pretty easy, okay? So just a little bit of background before we get started. We dealt with the wave-particle duality with electrons, remembering this formula right here. Now, we talked a lot about this formula in previous videos. If you have not seen me talk about this, you may want to go back and look at some of those videos because they are going to be very helpful for this. So I'm going to talk as though you've looked at the video so you know exactly what I'm talking about. Remember, this is wavelength. Right here, that's lambda, Greek letter for the little lambda, little length, wavelength. Planck's constant right here, mass, velocity, so momentum. Basically, the bottom line is wavelength and velocity are inversely proportional, and wavelength and mass are inversely proportional. So something big, if m is big, you're dividing this by a big number, this wavelength is going to be very extremely, like, infinitesimally small. So something like me or something like you who's like more than probably 20 kilograms, we're not going to have that big of a wavelength. But something very tiny like an electron, 10 to the negative 31st, I think, kilograms, that's going to have a noticeable wavelength. So like the smaller stuff gets, the more likely it is to act as a wave as well as something physical, so like a particle, okay? That's what this refers to conceptually. Using the equation itself is just plug and chug, okay? H is a constant, and you'll be given 2 of the other 3 variables, you just plug it and solve, okay? Now, electrons themselves, because they're probability functions. Remember Bohr said, like, hey, if this is the nucleus right here, it's like the sun in our solar system, we got orbits of electrons there, got another orbit there, and so on, almost like an earthquake symbol. Have you ever seen one in the newspaper, on the news or something like that? Or like ripples, and if you drop a stone in a lake and it makes ripples like that. Oh, those are going to be the areas where electrons orbit the nucleus. It ain't like that. That's the best Bohr could do at the time, but he was incorrect, and he only did it for hydrogen. If it gets something even more complicated, like, God forbid, helium, right? 2 protons, not just 1 proton like hydrogen, it gets really crazy. So, you have what are called 4 subshells, okay? Now, the 4 subshells are basically little areas around the nucleus where electrons can be found. They're not 2-dimensional rings like orbits of the planets orbiting the sun. They're 3-dimensional, okay? So there are spaces around the nucleus. The first one is the S, and I don't know, my purple has died, and there's no reason for it to have died. That's what I'm getting now. That's terrible. Gotta go with the blue. I should be using the pink, but I'm saving that for you in person. So. We have the S subshell. Now the S, how you can remember it is it's like a sphere, okay? I don't know why it's unfocused right there. So, S is a sphere. So, if you think of just like a balloon around the nucleus, that's where the S subshell exists. It's closest to the nucleus of an atom, and it's anywhere in that sphere is where the closest electrons to the nucleus, physically, location-wise, can be found. Okay? P. Now I'm going off of memory on this. You don't really need to know what they stand for, but I believe P stands for primary or principal, maybe meaning first. But it's not really first because the S is first. But it's a, let's go. It's more important that you remember just the letters themselves, okay? So, moving away from the nucleus, we got S, we got P, then we got D, then we got F. These are the important letters to know about electrons in atoms, okay? They go in one of these 4 categories, okay? And it depends on the row of the periodic table that they're in. Basically, it depends. The location of an element is going to determine how many of their however many electrons they have fall into this or this or this or this subshell, okay? So here's what I'm talking about. And I'm going to give this to you in the perspective of a periodic table. You should have a periodic table in front of you when I'm talking about this, so pause the video so you can get a periodic table, and I'm gonna, in the meantime, draw one. So it makes more sense if you're gonna have a real thing looking at you in the face rather than me just rambling on about it, okay? So in the meantime, I'm gonna draw one. I'm gonna pause the video, and when I come back and you hit play, we should both have periodic tables. I'm gonna draw a rough sketch of one. You're gonna get a real one loaded up on a computer, or maybe from your textbook, or from your notes. Be right back. We're back. What you're about to see right now is the worst drawing of a periodic table that still includes all the important info that you will be able to understand. Here we go. I know. Basically what I did is this. I did the first row for sure. And then I even did the second row from memory. I was pretty proud of myself. We got lithium, beryllium, boron, carbon, oxygen, nitrogen, fluorine, and neon. And then the third and fourth row. Okay. So now, what you'll see here is that the first 2 columns on the left of the periodic table are the alkaline metals and the alkali metals and the alkaline earth metals. Okay. Any elements in the first 2 columns on the left of the periodic table have their outermost electrons, and that's the key. The furthest electrons away from the nucleus, which are called valence electrons, V-A-L-E-N-C-E, like Valencia, but without the I-A at the end. It's like an E, valence electrons. They're going to have their valence electrons here in the S orbital, not the orbital, S subshell, okay? Now, anything ending in the right 6 columns of the periodic table, boron's column all the way to helium and neon's column, okay? Anyone that ends in there is going to have its final furthest away electrons from its nucleus in the P subshell. Anything that's a transition metal, okay, starting with element number 21, okay, the first 20 elements only have S orbital electrons and S subshell electrons and P subshell electrons. Starting with number 21, anything in here is going to have D's as well, D subshells. And then, you know, those that are at the bottom of the periodic table because they really fit in right here, but they like say, oh, 57 to 71. And then they at the bottom, they expand them out. It's almost like a pop-up menu on a computer or something. Those are called the actinides and the lanthanides, like where uranium lives and like lawrencium, berkelium, all these synthetic ones like neptunium, plutonium, all the very, very high, supermassive, high-numbered elements. Those have electrons in the F orbitals. Now, I keep saying orbitals instead of subshells, and they're very easy to confuse. So remember, SPDF are subshells. So now that you have this on your periodic table, hopefully you've marked this, the S, the P's, the D's, and the F's, their regions, okay? I'm going to tell you some more info about them, and I'm going to show you an example of why this stuff is important, okay? So, keep in mind, ending in S are the first 2 columns on the left. Any elements in them, no matter what period, and by the way, the periodic table, I don't know if you knew this, period just means horizontal row. So we call this the first period, second period, third period, or first row, second row, third row, etc., like that. P, subshells, the right 6 columns. The third through the 12th columns, and with the D orbitals, D subshells, I keep saying that, D subshells technically, and finally, the Fs are in the special, super weird ones, the actinides and the lanthanides. So, that being said, This is just background information. It may not make a bit of sense yet, but I promise you it will. I'm gonna pause the video again and give you an example of what kind of questions you'd be asked, why this is important, and so on. And I'm also gonna tie in orbitals actually, because hey, I've been saying it enough fraudulently, so let's see what an orbital actually is. I'm gonna erase this and I'll be right back.